In this question, one of the indications that is given to you that they are applying one sample t-test. One sample t-test is applied when sigma is unknown. They are testing mu equals 12 against mu is not equal 12. So here is H naught, mu equals 12 against H1, mu not equals 12. And they are asking you to find the missing value. The important information is that the sample size is 10. The sample mean is 12.564. The sample standard deviation is 1.1859. A tricky point is sometimes in exam, instead of standard deviation, they give you the standard error of mean. What is the standard error of mean? Yes. Sometimes it is actually sigma over square root of n. Sometimes they give you standard error of mean. If they give you standard error of mean, from standard error of mean, you can get sigma by multiplying the standard error with the square root of n, with the square root of 10. So you can get sigma from there. Then they give you the value of t. Of course, they obtain the t using this formula, which is 12.564 minus 12 over 1.1859 divided by square root of 10. They got it 1.504. After finding the p-value, the final part is to calculate the p-value. So for the p-value, you need to look at the sign of H1. What is the sign of H1? Two-sided, 2 times T9 more than absolute of 1.504. Now go to the T distribution with 9 degrees of freedom and look for the area above 1.504. So we go to the T table. With 9 degrees of freedom, with 9 degrees of freedom, I'll use this color, with 9 degrees of freedom, and look for 1.504. Where is 1.504? So the area above 1.504 is between 0.05 and, which is not p-value yet. So from the T table, you got this, which is not p-value yet. To make it p-value, what do you need to do? Multiply it by 2, which corresponds to, which should correspond to something between 0.1 and, which corresponds to this. If the p-value is between 0.1 and 0.2, of course, it's between 0.1 and 0.25, right? So it corresponds to this one. None of the other options contain even the portion of that p-value. The region for your p-value is from 10% to 20%, correct? None of the other 4 options contain any region from 10% to 20%. Okay? If there was any option, you could have been confused between the two, and in that case, both of the options could have been correct. For example, if option A was from 5% to 15%, now there is a region of p-value from 10 to 15% that belongs to option A also. In that case, you can claim that option A is correct. It will not be wrong. These 4 options are wrong because none of the area region of p-value belongs to those 4 options. I think they used a different table in this this one where it was between 0.05 and 0.125. Then they multiplied, and the table was a different table. For this table, I think the last option should have been 0.12, 0.2. But anyhow, next question says that the United States Golf Association tests the balls for whether they are okay or not. The balls are tested for the weights: diameter, roundness, overall distance. The overall distance test is conducted by hitting the ball with a driver swung by a mechanical device using a random sample. Now is the important information. What is the size of the sample? 227. It achieved that the mean distance, the question is about mean or proportion? Mean distance came out to be, which standard deviation is this? Sample standard deviation or population standard deviation? What is the claim? Can you support the claim? Can you support the claim that here is the claim? What is the claim? Write the claim in terms of notation. What is the claim in terms of notation? This is the claim. What is the opposite? This is H0. This is H1. Now find the p-value. They're asking you to find the p-value. By the way, which test will you apply in this case? Go to the second last slide of the chapter where we give you the map for choosing the test statistic. There were two cases under mean, when sigma is known and when sigma is unknown. You remember that? When sigma is unknown, then you look at the sample size, if the degree of freedom is available in T or not. Look at the sample size in this question. Do you think 277 minus 1, which is 276, do you think it is available in the T table? No. So the test statistic you will use here is which comes out to be 277 minus 280 divided by 12.06 over square root of 277. Calculators. The mean is 280. Where did I take 277 from? Sample. Oh, 282. If I knew this was one of the possible mistakes, I would have put that in the options also last semester. Round it. So it's approximately 2.76. Look at the sign of H1. What will be the expression for p-value? Is it one-sided or two-sided? So no multiplication by 2. Okay. If it is two-sided, it is 2 times probability. So one-sided means probability of Z less than or more than? More than, because H1 is more than 2.76. If it was less sided, p-value will be Z less than 2.76 or whatever value you get. If it was two-sided, it will be 2 times probability of Z more than the absolute value, whatever you get. Okay. So what is the probability of Z more than 2.76? Go to the Z table. You can do 1 minus, or you can use the symmetry of the distribution. It will be the same as less than minus 2.76. 0, 1, 2, 3, 4, 5, 6. It will be 0.00289. Or you can take the value from the positive side and 1 minus. It will give you the same thing, 0.00289. So the answer is 0.00. Is it there? Yes. 0.00289, which corresponds to option C. Any question? Question number 10. A researcher claims that at least 10% of the football helmets they have flaw. Just to make the question easy, they also gave you the notation. But what if they don't give you the notation? From the statement, you should be able to make the notation that the researcher claims that at least 10% of the helmets are defective. So P is more than or equal to 10% was the claim. then the opposite is that P is less than 10%. So a sample of 200 helmets, this is N. The question is about mu or P. It's easy to judge because the notations are given to you. But remember, if the notations are not given to you, you should be able to judge from the statement of the question if the question is about mean or proportion. A sample of 200 helmets gave you 16 to be defective. So number of defective is 16. This means your N is 200. Your X is 16. So your P hat is 16 over 200, which is 0.08 or 0.08. 0.08. Does this finding support the researcher's claim? Use the critical value. They give you the critical value instead of alpha. Which test do we apply for testing proportion? Z or T? These are the only two tests we studied. Z test. So they give you Z alpha to be 2.62. So let us check what is the value of Z. It is 0.08 minus 0.1 over 0.1 into 0.9 over 200. And it comes out to be either minus 0.94 or minus 1.04. These are the two options I see. Minus 0.94. This means that these two options are straight away rejected because Z value is not minus 1.04. Okay. Among the first three options, what is the direction of H1? The critical region will be written by you. What is the direction of H1? Less than. So you will say reject H0 if Z0 is less than minus 2.62. This is the correct version of rejection region. If less than, you reject on the less than side. So which one of these correspond to the correct rule? Since Z is minus 0.94 and it is less than 2, you will not compare it with the
It was two-sided, right?
we reject H0 if Z, which is minus 0.94, is less than minus 2.62. Is it less than minus 2.62? No, it is not. So you should fail to reject H0. Look for the option. Yeah. You will not check the absolute. It's a one-sided hypothesis. You will not check the absolute. Write the opposite of this statement. Reject H0 if Z0 is less than. Write the opposite. When will you not reject?
He didn't mention the minus.
Maybe they missed the minus. So write the opposite. That means minus 2.62 is less than minus 0.94. Maybe they missed the minus here. Yeah, maybe the printing minus is missing. So this should be the correct. Reject H0 if Z0 is less than minus 2.62. It should be which one?
Minus. and it is less than 36.
This is what I was going to do. The option should have been something like this, not less than minus 2.62. That's why we failed to reject it. That's the correct statement about the decision. You have a z of minus 0.94 and it is not less than minus 2.62. That's why we failed to reject H naught. This is correct statement. We reject H naught. We cannot accept this one. We accept the null hypothesis. We never use the terminology except H naught. We have said it repeatedly. We never use the terminology except H naught. So discard that one. Option B is correct, but with little modification. Maybe there was a correction during the exam for this option. This is it. Let us leave the further practice till the end of the semester. I will bring more questions, but mixed questions from 9, 11, and 12 at the end of semester. Now let us move on towards chapter 11, which is regression. This chapter you have already tasted it in ISC 291. But the way you took it there will be completely different from the way you will take it here. The way I will introduce it, you might not find this kind of explanation even in the book. So I will start introducing the regression using a definition which is called mathematical relationship, or what we call deterministic relationships. Are you all aware of this relationship between the Fahrenheit and Celsius? You know that if you know the temperature in Celsius, you can find the temperature in Fahrenheit, correct? So suppose you have two variables. One of them is the temperature of a place in Fahrenheit, and the other variable is the temperature of the same place in Celsius. And suppose you collect some data on different buildings, their temperature in Fahrenheit and their temperature in Celsius, and you plot that data onto a two-dimensional scatter plot. Do you know what is a scatter plot? It's a two-dimensional scatter plot where x is on x-axis, y is on y-axis. If you do that for Celsius and Fahrenheit, this is what you will get. You will get a straight line where each and every single point will fall onto the straight line. What does that mean? That means they have a perfect relationship. If I give you the value of Celsius, can you give me the exact value of Fahrenheit without any error? Yes. These kind of relationships where you have no chance of error, and the relationship is something like y equals the intercept plus slope times x. No error. Y equals beta naught plus beta 1 x. Here in this example, the intercept is 32 and the slope is 9/5, right? So such relationship where if we give you the value of input and you can give us the exact value of output variable, these relationships are called deterministic relationships or mathematical relationships, exact mathematical relationships. So knowing the temperature in Celsius, you can calculate the exact Fahrenheit value without any error in this kind of relationship. And we have nothing to do with this kind of relationship in this course. Just for the comparison, I brought this first slide that regression is linked with this kind of mathematical relationship. Now we get to more practical situations. Non-deterministic relationships. Sometimes you have two variables. When you collect the data on two variables and you put them onto a two-dimensional plot, you see there is something going on between the two variables, but it is not exact, like this. Each and every point does not fall exactly onto the line. If I pass a line through these data, the line will go through each and every point. No point will deviate from the line, correct? But same is not true for this. This is the data on an example where we are trying to see the relationship between the cutting tool life and the speed of the cutting tool. This is an example from mechanical engineering where you have a cutting tool and the life of the cutting tool when the tool wears out depends upon at what speed you turn on the tool. If you turn it on higher speed, it will run out quickly. If you turn it on slower speed, it will run out late. So there is a negative relationship between the two variables. If the speed is high, the life will come down. If the speed is low, the life will in general go up, but not a deterministic relationship. If I tell you the speed of a tool, can you tell me the exact life of that tool? But you can give me more or less a rough idea about that one, right? With subject to some error, subject to some error. So these kind of relationships are called statistical relationships. We call them non-deterministic relationship. And the difference between the deterministic and non-deterministic relationship is just a very small difference. That difference is this term. For the deterministic part, you had y equals beta naught plus beta 1 x without error. Now here you will say that we can give you a guessed value of y, but subject to some error, plus or minus something. And that epsilon can be positive quantity or it can be a negative quantity, indicating that the actual point can be above the line or it can be a little below the line. So let us quickly read what's written in the slide. You consider the relationship between the tool life and the tool speed. As the cutting speed increases, the tool life tends to decrease. However, the individual points, they do not fall exactly onto the line. These kind of relationships are called statistical relationships. The scatter plot is telling you that the points are spread around a line. You can pass through a line, but there is random variation around the line. Although the trend is there, the general trend is there, but knowing the cutting speed will not allow you to give the exact value of the life. You can only predict the value of life. Now at this point we have reached to understanding level what are the statistical relationships. Now if I give you this scatter plot and I ask you to pass a line through these points, can you pass a line through these points? How many lines can you pass through these points? I can pass through this line. Okay. I can pass through this line. I can pass through this line. How many more lines can I pass through these data? Infinity. Which one, which line would you prefer? Out of these three, for example. Too technical. Among the three of them, which one would you prefer now? Why red one? Because it is takes more point, or what we call it's closer to the points. Closer to the points, right? And what is the distance between the point and the line? What is the distance? When I say it's closer to the points, how do we measure the closeness? From the distance, right? The distance of the point from the line. And what is the, somewhere on the slide, I have written the notation for the distance between the point and the line. Epsilon. So you will pick the line that minimizes the total distance of the points from the line. So if I define my objective function to minimize this guy, will it work? Minimize the sum of errors, where some of the errors are positive, some of the errors are negative. There can be many lines that will satisfy this. Even that blue line, I think it is satisfying that criteria. Some of the points are above the line, some of the points are below the line. I think if you take the sum of those errors, I think it will be around 0. So I think all the three lines that I made, they all satisfy that criteria. Why? Because the negatives are canceling the positives. Correct? How can you avoid that? Either square or absolute. What if I take absolute? No problem. But where will be the problem? The problem will be later you have to differentiate this function to get the optimal values of beta naught and beta 1. Differentiation will become a little difficult. So instead of absolute, I will define my objective function to be, which will do the same job for me. So once you know what is a regression model, this is a regression model. Okay, from this regression model, you have epsilon equals y minus beta naught minus beta 1 x, the distance between the actual value and the fitted value. Then the next thing is to get the best values of beta naught and beta 1. And those best values depend upon your objective. Most of the times, the objective is to minimize the sum of squares of errors. And if you do the derivation, which is not a part of this course, but if you do the derivation and you try to differentiate this function, with respect to beta naught first, then with respect to beta 1, you will have two normal equations. You solve them simultaneously. If you solve them simultaneously, you will get this result, which is given to you in the formula sheet, and you have nothing to do with the derivation of those formulas. These formulas will be given to you in the formula sheet. What you need to know is there is a mistake here. Jawad, you will send me an email today evening to correct this mistake in the slides before posting. Take a snapshot of this one or remember it. Slide number 6. The subscript of beta should be not. So how did we get these formulas of beta naught hat and beta 1 hat? The background story is that we are trying to minimize the distance between the points and the lines, the squared distance between the points and the lines. Any questions so far? Yes.
Regression can only be linear.
No, it can be nonlinear.
But will we
No, it's not covered. The nonlinear regression or the polynomial regression is not covered in this course, but regression can be nonlinear. We try our best to keep it linear by transforming it to linear, but if it's impossible to transform to linear, we go to nonlinear. But there are many nonlinear models which can be transformed to linear and then fit this kind of regression. For those, go and register STAT 310. The name of the course is linear regression.
involve all of this angle?
Everything. It will involve everything, starting from basic simple linear regression all the way up to choosing the final model. Any other questions about the introduction of linear regression? What is S? Which S? This one, the formulas again, they are given to you. It's a function of X. It's actually the numerator of variance. You remember the formula of variance, summation X minus X bar whole square over N minus 1. So the numerator of the variance, we call it SXX. And the numerator of covariance, we call it SXY. Did we take covariance in this course? But the formulas, these are given to you in the formula sheet. And I will tell you what to do once you get a question in exam. Any question, technical question from the understanding? Let me repeat the whole story. The story is you have an unknown regression model. From this regression model, apparently, you see two unknown quantities. Where are those unknown quantities? There is a third one also. There is hiding somewhere. I will get back to that one in the next class. But apparently, there are two unknown quantities. Okay. These are called unknown parameters. Same problem that we have been dealing since the beginning of this course. You have a population. From that population, you have unknown quantity mu. How do you estimate that mu? You take a sample. Correct? Correct? You take a sample. So we took a sample. From that sample, we have the formulas for the estimate of beta naught and the estimate of beta 1. And that formulas are given to us in the formula sheet. How do we obtain those formulas? It does not belong to your syllabus, but there is a background story of minimizing the sum of squares of error. Why sum of squares of errors? You should know why not the sum of errors, why not the absolute of errors, why not other functions. The formulas are here. This guy is called SXY. You will see this notation in the slides, and this guy is called SXX. Similarly, beta naught hat is Y bar minus beta 1 hat times X bar. Let's move forward. After finding the regression line, which we will do in example, after finding the regression line, the next thing you might expect a question about the interpretation of these quantities. Once you compute beta naught and beta 1 from the sample, how to interpret those quantities. So after estimating beta naught and beta 1 in terms of beta naught hat and beta 1 hat, you will write the fitted model. The fitted model will be yi hat equals beta naught hat plus beta 1 hat times xi. And after writing the fitted model, what if they ask you to interpret this quantity B naught or B1? The answer to that one, B naught is what? The intercept. And B1 is what? The slope. So in context of the example that you are already discussing, where y is the tool life and x is the cutting speed, beta 1 will represent the average change in y due to 1 unit change in x. So if the cutting speed goes up by 1 unit, the life comes down or up depending upon the sign of beta 1 hat. If let's say beta 1 hat is minus 0.8, you will say that if the cutting speed goes up by 1 unit, the life comes down by 0.8 units, and vice versa. If this 0.8 was minus 0.8 was plus 0.8, you would say that if cutting speed increases, the life increases, which is non-realistic for this example. The second thing is the interpretation of the intercept. You have to be very, very careful about this one. Very careful about this one. The interpretation of beta naught hat will be done only if 0x equals 0 is in your data. What is the intercept mathematically? It's the value of y when x is. It's the value of y when the line crosses the vertical axis, correct? So you can easily say that it's the average tool life when the speed is 0. When the speed is 0. But you have to very, very cautious. Very, very, very cautious. For example, if I take the data on children from 0 to 10, x is their age, y is their height. Or let's say x is the height and y is the weight. Let's say I have a boy in my sample, 1 year old, and the height was what's the height of let's say a 1 year old boy, 1 year old 2 feet.
Size. Wait.
That's around 2 feet. 1 year.
Size. 1 feet and round.
Oh, other way around. Height is 2 feet. The weight of 1 year old boy is around, let's say 8 kilos. 8 kilos, let's say. If the height is 3 feet, let's say the weight is 12 kilos. Let's say height is 3.5. The weight is, let's say, 13 kilos. This is one boy. Let's say there is a boy whose height is 4 and the weight is 12.5, a slim boy, and so on. I have the data. Okay. I collect this data and I plot these data onto a two-dimensional graph where there is height here and there is weight here. And I have points something like this here. So in general, when height is increasing, weight is also increasing, but subject to some error, correct? And I pass a line through these data. And the line passes like this. And the line will not exactly pass through 0, 0. It will be either a little above 0, 0 or a little below 0, 0. This is 0, 0. The origin. Okay. Now, in this case, if you try to interpret the intercept, how will you interpret the intercept, this intercept? Let's say this beta naught hat in this case comes out to be 0.3. Or let's say 1.3. Will you say that a boy who has 0 height, his weight is 1.3 kilo? Mathematically, it is correct. That's the meaning of y-intercept, isn't it? But will you say that? Why no? X0 is not possible. How did you decide X0 is not possible? Looking at the description of the variable, variables were easy to describe. What if you have some complex variables and you're not the expert of that field and you cannot decide if that variable equals 0 is possible or not? So to be on the safe side, what we do is, if you observed in the data X0 is there, interpret. If you don't observe X0 in the data, don't interpret. So in your data, the data starts from 2, goes all the way up to, let's say, 9 kilo. Does 0 belong to the data? You will not interpret. You will say that we got 1.3, it has no meaning. You will say we got beta naught had to be 1.3, it has no meaning. But if you have a data set that starts from, let's say, -6, goes all the way up to 19, -6, -3, 1, 2, 7, 0 is within the domain of X. If it is the case, now you will interpret that it is the average value of Y when X is 0, because in your observed data, 0 belongs to the observed data. So here is the caution. Read the caution very carefully, that we will interpret the intercept only if a cutting speed of 0 falls within the data range. Otherwise, we will say that this intercept has no meaning. We got it -1.3 or whatever we get it, 2.7 or whatever, but it has no meaning. Whereas the slope, you will interpret it as usual. Any questions so far? Yes.
Can I take the slope starting from the origin and then find the best fitting line?
I don't get the question. Repeat the way you asked the question.
Just start from the origin 0, 0, 0, and then find the slopes that's close to most of points. It's the intercept is 0.
Indirectly, he's saying, can we force the line to pass through 0, 0? This is what you said, right? Yes, we can. We can force. In that case, you will be fitting, again, nothing to do with this course. In that case, you will be fitting this model with only one parameter. Here you are forcing beta naught to be 0, 0. This is the case when we clearly know that the intercept will be meaningless. For example, the height and the weight. If the height is 0, weight is supposed to be 0. We cannot afford a non-zero value. Okay. In that case, when you fit it, you will fit a line something like this blue line. Look. Which will not guarantee you that the sum of squares of errors are minimum. There will be a little more error than what you could have gone. Smaller squared errors. Blue line has bigger. Why you are going with more error? Because you want to put an extra constraint on your model, an extra condition on your model, that because my intercept doesn't make sense, I don't want to have the intercept. So that's an additional condition on your model. So that you have to pay the cost against that extra condition, which is that your sum of squares of error will be a little higher. Again, nothing to do with this course. Let us move on to the main thing, question. When you get a question from regression in exam, the available information will be given to you in either of the two ways, where the one that you see is less likely. The one I'm going to tell you now is more likely. Either you will be given the data on the two variables, or you will be given the summary of the data in terms of these 5 numbers. These 5 numbers. What did I say? In exam, either you will be given 2 columns of X and Y, or you will be given those 5 numbers. The sum of X column, the sum of Y column, the sum of column where you multiply x and y, the sum of x square column, and the sum of y square column. If they give you the summary of the data, it's much easier. If they don't give you the summary of the data, you are supposed to find the summary of the data by creating 3 new columns. What 3 new columns? You will create a column of x multiplied by y, in this case row, not column. You will create a row of x square, you will create a row of y square, and then you will find the sum of all the 5 rows or 5 columns if you write down the data in terms of column. Clear? So either they, most probably they will give you the data. Even if they give you the data, they will give you the summary of the data in terms of summation x, because it takes a lot of time to on calculator to compute the 3 new columns and find the sum. So once you have these 5 numbers, the next task is to find the 2 summary numbers. SXX, which is summation x squared minus summation x whole square over n. This is the numerator part of variance. If you divide this thing by n minus 1, it becomes variance. But we'll not do that. Here we don't need variance. Let us stop here, and I will discuss this example thoroughly in the next class. Let us talk about part 1. We constructed a scatter plot for the above data. Can you comment on the nature of relationship between these 2 variables, which are, what are the variables? What are the variables? X is the operating temperature. X is the operating temperature and Y is the process yield, process output. So if the temperature is increasing, the yield is going up in general, right? So it's a linear, strong linear positive relationship. Why did I call it strong? The points are very close to the line. What is the difference between these 2 scatter plots? Both of them are linear. One is strong, one is weak. One word is missing. Positive was missing. Oh. The top left is strong linear positive. Top right is weak linear positive. Bottom left is strong linear negative. Bottom right is strong weak linear negative, and this one is strong non-linear. We don't know positive or negative. It's a non-linear relationship, and in this course we will not talk about the non-linear relationships. Okay, this is a very strong non-linear relationship. All the points are exactly onto the curve. It's a quadratic relationship, but if you find the correlation for this data, it will be 0. Exactly 0. Go and try to find. I'll give you the data. Go and put this data into Excel sheet, make a scatter plot and find the correlation for this data. You will find that the scatter plot will indicate to you a perfect relationship, perfect quadratic relationship, and the correlation will be exactly 0. Because the correlation measures what? What is correlation? Did you take correlation ever? ISC 291, correlation. What is correlation? Not the relation. Not how strong. Not the relation. Correlation doesn't measure the relationship. Correlation measures the strength of linear relationship. Only linear, only linear, only linear. In this case, the relationship is very strong, but the correlation will be 0. When the correlation is 0, can you say that there is no relationship between the variables? No, you can say there is no linear relationship between the variables. We will discuss these points in detail in the next class.